control design, how good or my control design is. You can express it in terms of your frequent response functions. All right, this matrix equation motion in a simple form, and in the math matrix, we have a stable matrix, we have Stefan's matrix, and again, we all assume they are the positive or positive definite, semi-definite. We have equal 0 or equal 0 there. But math matrix is always 0, larger than 0. We talked about this positive definite earlier, so I don't want to talk more. And if I, this comparison, for single degree freedoms, m larger than 0, 0 larger equal than 0, k larger equal than 0, with 2 degree freedoms, this becomes matrix. M is a 2 by 2 matrix, zeta is 2 by 2 matrix, k is 2 by 2 matrix. And this is all 2 by 2 matrix, and we are all matrices. And matrices, we already know that m larger than 0, that's positive definite. Zeta larger equal to 0 means that's positive semi-definite. Okay, write it down. Okay. In the matrix case, this is the definition of metric theory there. So I'm going to say that larger than 0, we'll call this is positive, definite. Like z larger equal than 0 and k larger equal than 0, we call this some people call positive semi-definite. Semi-definite. That means we have equal sign here. Now there's a possibility that that equal to 0. Okay. For this case, we are called the positive definite. For this case, that's positive definite matrix, and k is also positive definite matrix. If k larger than 0, k1 larger than 0, k2 larger than 0, and k3 larger than 0. For any 0, 0, 1, and 0, 2. This is the definition of positive definite. And the same thing, 0, 1 larger than 0, 0, 2 larger than 0, 0, 3 larger than 0, and this zeta is also positive definite. And that system will be the stable system. If all matrices are positive definite, if all matrices, if we don't have this, if all, then this all positive definite, and there's no semi here, and there's all, if they're all larger than 0, they are all positive definite. So they are all positive definite. And if they are all positive definite, then what happens? The system is a stable system itself. The system is a stable system. So this is, in this we call asymptotically stable. The system is like this, we call asymptotically stable. That means very stable. That means all the system poles have negative real parts. That means all the poles. This system means all poles have negative real part. That's what it means. It's easy to prove that I don't have enough time to prove it for you, but you have to remember these definitions. What definition of positive definite? The definition of positive definite is for any vector Z1, Z2, and if you multiply them together become a scalar, and they are positive, and this is called positive definite. And this is the definition of the matrix theory. It's very useful for the mechanical system like this. And in mechanical system, we know that if K1, K2, and K3, they're all positive, and Z1, Z2, and Z3, they're all positive, we know this system is a stable system from physical sense. And mathematically, how you say this is positive, how you say this is a stable system, you look at the massive matrix, you look at the stiffness matrix, you then look at the bending matrix, and all these three matrices are positive definite, and then we know that this is the same way that this is the system that's a stable, asymptotically stable system. And physically, that's on the bottom side of these slides. Okay, that's harmonic excitation. Now let's look at harmonic excitation again. We always look at harmonic excitation, and then we have the EU exponential I omega t. Again, this exponential I omega t doesn't make any sense, but E cosine, this is what I mean is E cosine omega t. Alright? So, but again, to solve this, it's easier to use EI omega t. So if I use EI omega t, if I solve this, then I will substitution, I got the following system here. Then I have n I omega square plus zeta I omega plus k, and W E I omega t equal to U E I omega t, that imply W equal to parenthesis bracket minus omega square n plus I omega zeta plus k, the bracket, and then inverse, matrix inverse U. Let me take a breath. Am I talking too quick? Okay? The speed is okay? If I use slides, I can keep going as quickly like this, you know. But I assume that you know the matrices. 我是假设你们这个对这个 matrices 都熟了哈，所以I did not really give you time to refresh your memory about the matrix theory, but I give you notes already. And we might come back to talk about that later if we really need it. Okay, so from here you will be able to see how powerful of the exponential function. So EI omega, sub in EI omega into the differential equation, you can write this in terms of the complex number like this is very quickly without going to cosine and sine. Every time you differentiate a cosine becomes a sine, you differentiate sine becomes a cosine, and we are not the same thing, so you got all kind of problem. But if you use EI omega t, differentiate of EI omega t is omega t and EI omega t with I omega EI omega t, so it's much easier to differentiate an exponential function rather than a cosine. Okay, that's the reason why people always use EI omega t to represent a harmonic excitation. So you can see how powerful is this. Okay, the steady state solution was this, is look at very complex, just like I showed you the TMB. It's the same thing like I showed you about TMB. And now this is a matrix the same as the matrix in the TMD, and we have a Z11, Z12, and Z12, and Z22. Again, this is also a symmetric matrix. A symmetric matrix inverse, also a symmetric matrix. So this is the inverse. The symmetric matrix inverse will become a Z11, Z12, and so on, is also a symmetric matrix. So a matrix inverse for 2 by 2 is easy. Just a determinant of this matrix. That's a Z11, Z22 minus Z12 square. And then the first element becomes Z22, the last element becomes Z11, and then this location becomes minus Z12 and minus Z12. That's all. It's easy for the 2 by 2. For 3 by 3, one was just easy anymore. So I don't show you for 3 by 3, I cannot show you for 3 by 3. You have to use the Scilab or MATLAB to do it. Alright? But just give you a concept of a matrix. 2 by 2 is a matrix. 3 by 3 is also a matrix. 4 by 4 is a matrix. The same way we solve this. Okay, so I have W1 now. I have W2. But I have 2 input. One is U1 input, one is U2 input. Look at that. I have U1 and U2 here. So, now here I have W1 equal to omega and U1 minus Z1 to omega U2 and Z11 omega Z2 to omega minus Z1 to omega square, and W2 is equal to Z11 omega V1 plus Z2 omega U2 and Z11 omega and so on. That you have W1, your W2, your U1, your U2. U1 and U2. So, because of that, let us look at the real example. Don't forget we have W1 here, I have W2 here, I have U1, I have U2, so I have 2 input and 2 output. And if I have N1 equal to N2 equal to 1, Z1 equal to Z2 equal to Z3 is 0.011% ranking. And I have K1 equal to K2 and equal to K3 equal to 1. Right? In your exam, in your homework problem, the second homework, all the problems I give to you, like M is 1,000 kilogram. That's a real example. That's not an imaginary number, you know. But this is just an imaginary number. This is just give you some idea of the steady state response. Okay, my steady state response is this. You sub these values N1, N2, Z1, Z2, Z3, and K1, K2, K3 into the steady state response, then you will get this. Wait a second. Then you will get this